Hey, good morning, all my chemistry people. Time for once again another installment of Chemistry at Home. Before I get going, I want to talk to you a little bit about the regents, as there's some noise about what's going on down in Albany about decision making with the regents and our wonderful COVID-19 situation. I'm not really going to say anything just yet. There have been some decisions that have been made, but if you can imagine, things are not perfectly clear what we can and can't do and what it actually means. So I will let you know as soon as I find out and get things like ironed out. When things are definite, I'll let everybody know what the situation is as far as it pertains to us. I have a feeling things might be different for each school district, for each area. Nothing's, if you can believe it, nothing is set in stone in this ever-changing COVID-19 world that we are living in. So I'm aware of it. I will update you as soon as I know something solid for sure. I will let you know. So we're still here. We're still learning chemistry. So with that, what do you say we dive right in? So what we're gonna talk about today are acid and base reactions, and really, guys, there's only two that we need to worry about because for us, acids and bases only do two reactions. Um, and then this is gonna be sort of like the end of the first half of this chapter, and the second half of the chapter is how we apply those chemical reactions in um, analysis, really, because we use acid-base reactions in a lot of analytical things. So thus far, we spent our first lesson talking about all the characteristics of acids and bases. And if you've noticed, everything that we've done so far is more of like an expansion of all those little details that we talked about way back in our very first lesson. Like, well, first it was just like characteristics, and then we went over what makes a substance an acid and what makes something a base. You remember there's two ways we go about that. The first is the Arrhenius theory. Acids make an H, bases make an OH. And then there's the Bronsted-Lowry. Acids donate a hydrogen ion, or like they make a hydrogen ion. Bases absorb that hydrogen ion. And you remember, Bronsted-Lowry only works with a system at equilibrium, right? Right. Then we went into, man, what did we do then? Was it naming and strong and weak? I think that was it. Naming. Wait. First, let's do strong and weak. Strong, if it's ionic, it's gonna be strong. If it's carbon based, it's gonna be weak, and it's gonna be weak because, and you'll see like a little equilibrium sign, and that makes it a weak acid or a base, and that means that they don't break apart constantly, so they're only like making hydrogen and hydroxide ions like part time. I think what it comes out to be is about 30% of the time hydrogen and hydroxide ions are available. But that's what makes them weak. They're weak electrolytes, they're weak acids and bases. They don't really work all that powerful. But in the world of science and chemistry, strong and weak does not depend on concentration. We have a whole separate thing. We did a whole chapter 7 to talk about concentration. That's not what makes it strong and weak. It's how well they break apart when you put them in water. Dug, awesome. And then we went into naming diatomic acids. That's a hydrogen and a nonmetal. Hydro, whatever, end it with ic. Bam, done. And then the complicated one is if you have a hydrogen bonded to a polyatomic ion, all you gotta do is take the name of the polyatomic ion and the ending there, ate to ic, ite to us. You just change ate to ic and change ite to us. You change ate to ic and change ite to ite. See, now I need my ruler. I need my big like periodic table so I can hit it and I'll smack the ruler on the table and break it in front of someone's face and frighten people. It'll be great. I miss the good old days. Anyway, so what we're gonna look at now are the two reactions that acids and bases do. First, we're gonna go with the easy one, and this basically means if you take an acid and you put a metal in it, you're going to make hydrogen gas because lots and lots of bubbles. I don't know if you guys, I think I said this before, but do you remember when I put zinc in with hydrochloric acid and made lots of bubbles and I blew up that can? That was so awesome. And in the very beginning of the year, I did it with calcium. I mixed calcium with water, but there was actually just a teensy little bit of acid in there just to kind of help it go along a lot faster. Bubble, 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 bubble. And all that is it's just like an acid reacting with a metal. And here's the deal. Acids and metals react to form hydrogen gas, okay? And but not all metals do that. So what we're gonna do is we come down to this little Jimmy. Whoa, what happened there? We're gonna come down to this little Jimmy John right now. Table J. I don't know what's going on with the screen. Right here, table J. This guy. Table J is going to tell us which metals will and which metals will not react to form hydrogen gas. It's really simple. Anything above hydrogen right here, right? Anything above hydrogen will react. So like I kind of cut this in half because it's a very, very long table. So for example, if Ni stands for nickel. If I took a lump of nickel and I plunked it into some acid, the nickel would start to bubble, fizz, fizz, and hydrogen gas would be given off. That's all we really need to know about this particular chemical reaction. Now the reason why that works is because the metals above hydrogen have a higher electronegativity than the hydrogen, and so what happens? All right, nobody's perfect. It's errors but human, and you know I'm the most human teacher you're ever gonna have in your life. Exactly what I said, only completely opposite, okay? The metals, I have it written in front of me too. The metals have a lower electronegativity than hydrogen. I had a hydrogen in my brain. The metals have a lower electronegativity than hydrogen. So what that means is when you take a hunk of metal and you plop it into an acid, that hydrogen ion can pull on electrons really good. And that's awesome because it's got a +1 charge. And you remember the electrons in a metal, highly mobile, right? That's kind of one of the things that makes a metal. They're all on like the lower left-hand side of the periodic table, which means they have very, very low electronegativities and very, very low ionization energies. And what that tells us is that metals can hardly hold on to their electrons. They fall right off. I mean, that's why electricity works so good through a wire. Electrons just pop right off. So when you have a hunk of a metal that can barely hold on to its electrons, and you put it next to a hydrogen ion, which has a full +1 charge, man, that hydrogen just rips the electron right off of the metal, makes an H2, and bubbles off into the atmosphere where we light it up and watch giant orange fireballs. It's beautiful. But yeah, I mean, that's why it happens, okay? You need to know what happens, and you need to know why. So metals above hydrogen on table J will react with acids to form hydrogen gas because those hydrogen ions have a very high electronegativity and metals tend to have a very low electronegativity. So the hydrogens just rip off the electrons. However, we are talking about nature and we're talking about chemistry. So you know, man, you know this is not always the case. And here it is. These guys right here, copper, gold, that's silver and gold. Copper, silver, and gold. Those three metals, if you put them into an acid, they actually do not react with acids. At least they don't react right away. It's one of the things that made like gold so amazingly popular to our ancient ancestors, because it doesn't really react with things. So that's also why we use plumbing, copper for plumbing, because water can oftentimes be a little acidic. And if you remember, way back at the very top of the notes, we talked about how all water has some hydrogen ions, remember, because they're always smacking into each other and breaking apart. So if copper did indeed react with acids, we couldn't use it for plumbing because that small amount of acid would etch away the copper and it would like melt all of our plumbing, and it makes flushing toilets difficult if you don't have plumbing. So yeah, there's that. Complicated? No, I'm going to go with no, this is not complicated. Any metal above hydrogen on table J will react with an acid to form hydrogen gas that we light on fire for educational purposes. All right, the next one, I forgot. Wait, we got these things. Let's do a couple examples because this is the kind of thing that you're going to have to be able to do, right? Okay? So here we have HCl. You will notice that it is indeed a hydrogen, or I'm sorry, an acid, because it starts with hydrogen, and we have calcium. So let's go over to our table J right over there, and let's find. So that's our acid. Here's our metal. Let's look for calcium. Oh, there it is right here. Bink. All right, calcium. So calcium appears to be above hydrogen on table J. It looks like this is going to happen. So the first thing we're going to make is hydrogen gas. Right? So that I know. I know that we're going to make hydrogen gas. Now the next thing. Here's the thing. Let me go like this. What I like to do for this, so we have the acid, we have the metal. So what's going to be left over? So remember, my eyes are terrible. The whole like flippity floppity thing. So what I like to do is I'll scribble out this H. Right? Now I know what I have left over. Right? So the two things that I have left over are calcium and chlorine. And so this compound here is going to be made out of calcium and chlorine. Positive thing first and negative thing second, always. So I'm going to go to my periodic table. I'm going to look at calcium. I'm going to see that it's in group 2. Calcium will have a 2+. Can I do this on a computer? It's really bad. And I'll be left with chlorine. And chlorine, if you look it up, you'll see will have a -1. Right? You guys remember doing this on that lab that everybody hated? I'm like, well, you better get used to it. Here it is. This is why, because we're doing this for like till June. So we're gonna do the drop and flop, the flip flop, the flippity floppity fling, the crossover, whatever you want to call it. So we're gonna take the 1, goes right down there. We'll have 1 calcium, and that 2 goes right here. So my final, that is so bad. My little pen thing, I don't have my pen writer thing because I can't go anywhere because stupid contaminating the world if I leave my house. So that's how that works. You guys get what I'm saying? So there's that one. This next one, HNO3, definitely an acid, and manganese. Manganese, I'm gonna look it up. It's got, I think, a couple of options. Let me see what we got here. Mn. Oh, it's not letting me do that. Oh well, we'll just stay right here, guys. It's gonna be a +2. I looked it up on the periodic table. So first thing I'm gonna make here is H2. H subscript E2, right? Now, what I'm gonna get rid of here is I'm gonna get rid of that H. We'll do it some other time when I'm not recording. I'll just clip this part out. Just hold on. All right, take 2. All right, I'm gonna edit right back in. Plus things plus. We've got Mn. Now, something we need to remember is that Mn is we're gonna have a +2 on that bad boy right there, right? And then the other thing that is left over is this NO3. Now the NO3, oops. I'm not really sure what the charge of the NO3 is. There's a couple things that like we can do here, to check out what the charge is of my NO3. One, we can just look it up on the periodic table. The other thing is we can see right here. You see how it's bonded to only 1 hydrogen? That means that the NO3 can only have a charge of -1. That's the only thing it can possibly be. Do you understand what I'm saying? Because if NO3 has 1 hydrogen, that's only 1 plus, so the NO3 has to be a -1 to make it canceled out and equal to 0, right? All right, so if Mn has a +2 and NO3 has a -1, that means my manganese will have a subscript of 1, and my NO3 will have a subscript of, say it out loud. Nobody's listening anyway. Right, 2. So let's scrub these things out. And remember, we're not gonna like just put it at the bottom. We're not gonna say it's NO32, because if we said NO32, that would be just silly. So it would be MNO3 2. Dug, done, awesome. Let's look at this one. All right, here's an acid, very easy to see. Sulfuric acid, fun. And here we have copper. All right, sulfuric acid. It's a diprotic, nasty acid. Let's see. Will the copper? Do you guys see? You guys see what I see? Nope. Not happening. Look, hydrochloric acid. Doesn't matter what kind of acid it is. Nope. Nope, nope, nope. Nope, nope. It's not happening because copper's below hydrogen. Easy peasy lemon squeezy. Again, which three metals? Copper, silver, gold. Those are the three exceptions, so those are the ones you just kind of got to lock onto. You dig what I'm saying? Awesome sauce. All right. I think that's it for what happens with acids and metals. Pretty simple. Hydrogen gas, and then like there's a leftover. Oh, and these things right here, these guys, like the manganese nitrate and whatever, what was that? Calcium chloride. These things are salts because it's ionic and it's not an acid or a base, so it's a salt. You dig what I'm saying? Awesome. Moving on. The next one that we need to talk about now, this one here, this is like the workhorse of all of your acids and bases. This is like the brick that all of analytical acid base stuff is based on. So I'm gonna want you to like dial in on this one. So what we have is a neutralization. Now we call it neutralization because when we're done, we have a neutral solution. It is not an acid solution. It is not it's not an alkaline solution. It is totally neutral. Okay? Alkaline meaning base, basic kind of thing. So for a neutralization reaction, that is when every single hydrogen ion is canceled out by a hydroxide ion, and every hydroxide ion is canceled out by a hydrogen ion. And what we're left with is water and a salt, and that is it. Acids and a base makes water and salt. Acids and a base make water and, okay, and but the neutralization is when they completely wipe each other out. So you're not left with kind of an acidic solution or kind of an alkaline basic solution. It is like they're gone. All the hydrogens cancel out the hydroxides. You guys get what I'm saying? So here's an example where an acid and base makes water and salt, or salt and water, doesn't matter. Acid, base, salt, water. Do you see on this product side anywhere, do you see an acid or a base? Nope, because it's a neutral solution, right? The acids and bases are gone. That's all there is to it. Does that make sense? Where this starts to get weird is that we have to double check and watch, because it is one hydrogen and one hydroxide. Does that make sense to you guys? So what's actually happening here is like the actual, like they call it, I don't think I have it down there. The actual net ionic equation, like what's actually happening, like we're not, if we ignore the spectators, the ions that are doing stuff are hydrogen, which is hydrogen with a +1. Right? So you have your hydrogen ion. It's going to get mixed up with, or going to come in contact with your hydroxide. Right? Oops. You dig what I'm saying? Now, this is going to, like, it's going to make, let's see what I can do. Look, there's an arrow. It's going to make high quality H2O. You guys get what I'm saying? I don't think that was in our notes, but I really want you to dial in on that, what we call the net ionic equation. So in this here acid and base reaction, what we've got is this hydrogen and this hydroxide. These are what to get together to make our good old high quality H2O. You dig what I'm saying? And then these leftover things, these things like the sodium and the chlorine, they're just, that's what salt is. It's just the leftovers of an acid-base reaction. Does that make sense? But really, in water, these are aqueous, and this is just a sodium +1, and this is a chlorine -1, and they're both just floating around. But what's really changed here is that this hydrogen and this hydroxide ion, they're no longer ions. They're not floating around in solution anymore. They are dead and gone, and now they have made a water molecule. So that is why we are going to call this right here the net ionic equation of an acid-base reaction, because these are the ions actually doing like the work. And what's also really important for you to see, for what we get into next is that there is one hydrogen and one hydroxide here. It's a 1-to-1 ratio. Dig, dug, delightful. Let's move on to like a couple other things here, like examples. Oh, like this one right here. So there's your acid, there's your base. Guess what the first thing you're gonna make is? Yeah, good old high quality H2O. Now the question is, what is your salt? And I have an answer for you. This I have again come up with some things because my eyes are just. How about random color generator? Bam. Ooh, hold on, guys. I just chose Sentinel purple. That's not going to work out too well. Let's do like puke green. All right. So here's what I do. I know that an acid and a base are going to make water and salt. So I know that this hydrogen and this hydroxide are going to make water. So what I do is I scribble out the hydrogen and I scribble out the hydroxide. So now I see what's going to be left. I'm going to have cesium, and you see how cesium is on the left here? Cesium will be on the left over here too. And if cesium is attached to one hydroxide, I know that my cesium is going to be +1. God, I need my pen pad really bad. Right? And my NO3 it is attached to one hydrogen, so this is going to be -1. You with me? You guys see that? So what I'm going to end up with is CsNO3. I don't think I have a good eraser here, guys. Are we good? I think I need to just like. I think I need to like just kill this. CsNO3. Oop. Oh, you guys get the idea. I don't feel like drawing it. Anyway, moving on. Ooh. Oh, we've got a couple. Oh man, we've got a couple more. Now, ooh. Here's one. This is, see, I may have put this down here for a reason. All right. You want to dig into this one? Let's dig into it. So here we go. Acid and a base are the first thing that it's going to make. I'm gonna have I have a hunch, but the first product is going to be a high quality H2O. Excellent. And now I got to find what's going to go here. I'm not exactly sure, so I'm going to go get my handy dandy pencil thing. And let's not do puke green. Let's do Viking red. Why not? Again, what I do is I scribble out my hydrogen and I scribble out my hydroxide just so it's like not in my eyeballs and I'm not looking at it. You understand what I'm saying? So I've got bromine, which this bromine is attached to one hydrogen, so it's going to have to be a -1. Does that make sense? I don't have to look up on the periodic table. It's just like it's right there. Now that calcium, you might not know what the charge of calcium is. I don't either, but no matter because I know that calcium is attached to these two, like this 2 right here. You see that? So I know that this has to be a +2. I know it's a plus because it's on the left-hand side. I know it's a 2 because it has 2 hydroxides. So it's going to be calcium bromide. Dude, look at me draw with this thing. It almost looks like I'm in kindergarten. I'm getting better. But remember, there's a +2 here. So I'm going to need 2 bromines to make this a neutral compound. So hydrogen bromide, calcium hydroxide yield water and calcium bromide. Done. Easy. Not even scared. Hope you're not scared. I know I'm not scared. You scared? I ain't scared. I ain't scared of nothing scared. Not even a little bit scared. Kidding me? Not even a little bit. So this is why it was important for us to recognize like diprotic and like dihydroxy acids and bases because it can mess things up. It can mess the balance up and whatnot. Okay. So next one. Let's go. Oh, I forgot to balance that equation. That's okay. Well, let's balance this one because then look, we're done. H2SO4, KOH. You guys know what to do. The very first thing that happens is we're going to get some high quality H2O. I should have copied and pasted this, but I'm not that smart. So there's H2O. Now, what could I possibly have left over? First thing I'm going to do is I'm going to choose, I don't know what this one is. I'm going to get rid of the H. I'm going to get rid of the OH. So now I can see what I've got left over. So before I start writing, I see that my SO4 right here has 2 hydrogens. So that's got to be a +2, right? And that potassium only has 1 hydroxide, so it, whoa. Oh, geez. Hold on. Knuckle brain. All right. Wait, we're scribbling that out. I need a quick do-over, guys. This is going to be a -2 because it's on the right-hand side. It's not going to be a plus. I'm not done with my coffee yet. I am. That's really depressing. I'm still in a mess and I still haven't finished my coffee. So this is going to be a +1. So moving over to that side, let's check it out. We're going to have potassium because potassium goes first. It's going to be a +1. Then I'm going to have SO4. Oh, man, this is bad. I feel like it's so bad. All right, so this is this ion has a -2. So if there's a 2 here, I'm going to put a 2 to my potassium. There's only a +1 for this potassium, so I only need 1 SO4. That's supposed to be K2SO4. Man, don't judge. Don't judge. You're judging. I know you will. That's okay. I ain't scared. I don't care. Here's what I need. That's the end. Neutralization reactions. That's the one I need you guys to work on for me. There's gonna be a little bit more coming at you, and then we're gonna have a little bit of a break. It's gonna be nice. Just gonna make sure that we're doing the right neutralization reaction. It looks like this in your homework packet. Oh God, remember my binders? They ain't gone yet, people. This is what it's gonna. Whoa, that's what it's gonna look like, right? Because there's a couple different of these that we're gonna be looking at. So remember, these words have much knowledge. There's so much knowledge there. If you actually pay attention to this video, and I'm noticing that not everybody is, go tell people to watch the stinking videos. Read a little bit of that paragraph, work on that neutralization one, and bada bing, bada boom. That's gonna be it for you guys. Yeah, there will be more to come. I hope you guys are doing well. I'm feeling awesome, and yeah, maybe I'll see you in May or June. I don't know, man. Hope to see you soon. Deuces.